we can start.
Okay, so can you see the screen?
You can see. Yes, we can see.
Yes, okay. So see, this is, so Piali asked me to talk about this. And the thing is, I haven't worked with the pencil code in a couple of years. And then I foolishly said yes. And then I thought that, okay, I can probably still pencil code. But then when I look back at the pencil code, it doesn't look the same anymore, of course. So things have changed and I tried to adapt. And I found out that some things that I used to work with have bugs and I fixed them, but I can't check back because of some SSH problem. Anyhow, so what I am going to show you may not be completely correct, but may still work in principle. In the sense, okay, what it means in principle is not very clear. Okay, so but this is not really a lecture, right? This is extremely informal. So all of you guys have your computer in front of you.
Yes, I think we do.
And yeah. And you are going to basically, I'm going to basically show you various pieces of the code, okay? And trying to tell you how the particle things work. So as an example, I will take the thing I talked about in the morning, okay? And why would I do that? One of the reason being that this will show you how to add something new to the code that's part in the particle wise. And you should also know that the particle module is actually quite huge and it is not difficult to get lost. So I am trying to be within a narrow domain where we can keep some sanity in the discussion. Okay, stop me any point, rather stop me all the time. Okay, so we want to solve for particles in the pencil code, right? So then this irritating Zoom bar. Anyway, so these are the equations from the morning. So this is the momentum equation. This is the continuity equation or the density equation. And then comes the magnetic field equation. Whatever that is, that's not my main problem in the particle module. Okay. So this part of what you want the flow to be, you should use some sample. And the sample that I often start with is this sample called helical MHD turb. Okay. So do a PC new run and then do PC build, etc. to make sure that the sample works. Okay. So everyone is happy that I'm not going to talk about that. Okay. Is that fine? Okay. Hello.
Yes, yes, fine.
Yes. Having some response helps. Of course, everybody turns themselves mute, but still having some response helps. Because talking to just a computer screen can be somewhat strange.
Dhruv, now I think it is sorted, right? Screen sharing in the breakout room, we were trying to sort that.
Okay, so is everybody with me? So we are talking about the flow.
Yeah.
And the flow could be anything. For example, the part I am talking about is a flow plus magnetic field, and there is a force that is studying it and so on. And for this, I am taking the sample helical MHD turb. Okay. If you want a flow that is compressible, then you need to take some other sample. If you want a flow that is, say, magnetic field is done in some other way, then you need to take some other sample. Okay. If you want to include convection, then you need to take some other sample. But that's just part of the PDEs. and you choose your sample, you do PC new run, you do PC build, and you are fine. Now we introduce particles. So the particles come with typically two equations, because the equation of motion of the particle is typically second order, except the tracer particles. And I will tell you about them also. But most of the time, the particle behavior looks like this. dx dt is velocity and dv dt is the acceleration, which gives me the force. Okay. So if you want to just solve for particles, inertial particles in a flow, then the right-hand side will be what in pencil code way we call dust. So there is a huge amount of work on the dust, and there are different dust modules that you need to look at and so on. Okay. At the end of this, maybe that will also be clear to you. So then I have the dv dt, and then I have the electric field, and then I have the magnetic field. And this v is not the velocity of the flow u, but the velocity of the particle v. And then the delta function implies that the position that I am calculating the right-hand side, I have to take the quantities, the electric field interpolated from the grid itself. Okay. Now you remember that in the pencil code, we don't know magnetic field and we don't know electric field, because these two are typically not stored. What is stored is just the magnetic vector potential. Now, if you evolve the magnetic vector potential, there is no additional evolution for magnetic field or electric field. So these two then become what we call auxiliary variable. Okay. Variables that are not evolved, but evaluated every time. So this is the electric field and the magnetic field are fields. So they will have n cube resolution, but electric field is calculated this way, and the magnetic field B is just curl of A. Now, will this work? Hopefully. And now you need to interpolate. Okay. So remember the idea of the auxiliary field. So now I am looking at rest of what I am going to talk about involves also another sample, and I will tell you about it in a moment. So how does this work? Okay. So now I am looking at a sample, and let me, okay. Can you see my screen still?
Yes.
Okay. So in the samples, there is one called charged particle in MHD term. Okay. Let's go and look there. So as you know, in the samples, the most important things are two. One is the makefile.local. So let's see what is there in the makefile. This is MPI. This has ideal gas. This has hydro. This has density. No entropy, magnetic field, no gravity, forcing. We are using Fourier spectrum, Fourier way to calculate power spectrum. That's not so important. But I am saying particles are particles charged, and particle radius is particles radius. That sounds confusing, but it will become clear in a moment. But the other thing you need to remember is whenever you use particle, always use double precision. Okay, good. So this is the makefile.local. And then we have the cparam.local. So in the cparam, you see number of CPUs 4, number of processor in the Y direction 1, number of processor in the Z direction, whatever you obtain from this, number of processor in the X direction is 1. X grid is 64. This is basically a 64 cube simulation. And there are 30,000 particles. So that's the first particle quantity that you have. The other quantity is the MAUX contribution 6. You see, in the cparam.local file, this will look like it is actually commented out. right? This is because when you know about the pencil code somewhat now, there is a script that is running on the code before Fortran is used. And this is a script that is collecting lines like this, which will be not used in the Fortran code, but this will be used in the script to calculate, to construct another Fortran file that will be used within Fortran. So this is being explained somewhere else, I guess.
Dhruva,
So,
is this script Perl based or what?
Sorry?
Is this script that is running background, is this Perl based language or what?
It is Perl based, yes.
Oh, okay.
It is Perl based. It is not, I would say, not say it's running in the background. It's basically part of the compilation process to begin with. So when you do PC build, first stage is to actually extract such lines from all the files and then have another, basically construct an input to other Fortran files. Okay, so here I am mentioning the AUX contribution to be 6. 6 because 3 components of the magnetic field and 3 components of the electric field. Okay. Everything good so far?
Yes.
Okay. Now let me see how to get out of this. Okay. Okay. So let's see now. So here, now in other cases, for example, if you look at the sample helical MHD turbulence and look at the makefile there, you will find particles equal to particle stressor and particle stalker equal to particle stalker. Now the stalker part is a slightly scary thing, but don't worry about that. So when you have particle tracers, what does it mean? So these are basically Lagrangian particle such that their velocity is the flow velocity at that point. Okay. So in that case, you don't have 2 equations for every particle. You have 1 equation for every particle. So if you want to run tracer particles, it is simple. Just do it this way. Okay. In this case, we are using particles equal to particles charged and particle radius equal to particle radius, and I will return back to that. And here,
Dhruva, what was the difference between tracer and stalker?
No, tracer and there are both. So basically, you see, you have tracers, and now you may want to say at the position of every tracer, what is the statistics of the flow? Okay. You may want to say maybe the tracer particles sample only those part of the flow that has something special from the other parts. This is not true, but you can imagine asking such a question. Or you can say that if I am sitting at one point in a Eulerian flow and I look at the statistics of velocity gradients, okay, and at the same time I ride a particle and look at the statistics of velocity gradient, are these two going to be the same? You can ask questions like that, right? Then you need to calculate other quantities at the position of the particle. Now you may choose to calculate them not for every particle, but a fraction of them.
Okay.
So such are the stalkers. They're basically a bunch of variables which stalk every particle. And you can choose a certain number of stalker. If you choose the number of stalker to be equal to your number of particles, then you are stalking every particle. Okay. Is that clear?
But I may choose not to stalk any particle as well.
You can do that. Absolutely. You can completely remove that.
Then do I need this module? Then I don't need this.
Yep, absolutely. Then you can just remove this line because by default, this module is off. So you can just use particles equal to particles tracer. Okay. So over here, you have particles equal to particle charged and particles radius equal to particles radius. Here you cannot get rid of the radius. I will come to that. The radius is actually quite a, how should I say, bad way of doing what we are doing, but we have been doing it for too long, so we haven't changed. Okay, so now you see the auxiliary contribution. The 6 comes 3 from the electric field and 3 from the magnetic field. Okay. Now let's look at the particle module. So first quantity to look at is this one. So SR, let's see, SRC / particles and then charged dot F90. Okay. So in the first there you see MP var contribution 6, M auxiliary contribution 2. So don't worry about the M auxiliary contribution, just worry about MP var equal to 6. Okay. So this MP var equal to 6 means that you have 3 position and 3 velocities. Okay. So if you were using tracer particles, then it would be MP var equal to 3. Okay. Up to this point, everything is clear, right?
Yes.
Yes, thank you. Okay, so now let's slowly walk through the particle charge module. Okay, some points I'll be fast, some points I'll be slow. So stop me and ask any question. Let's just read this. Okay, so particles, module particles, fine. And then various things goes on, lots of parameters, and then so on. See, basically this is copied from the other dust modules and then changed. So some of the old comments and so on has remained and no one bothered to clean it up. So in all the particle module, you first get something called register particle. Okay. So basically you are telling it how many new variables you are adding to the problem. So this is this thing called NP var. So you add XP, YP, ZP, a vector for 3 positions and a vector for 3 velocities. Okay. Then you say initialize particles. Now initialize particles and init particles are 2 different things. Just remember that. So now you remember we talked about interpolation. So one of the things you do in the initialized particle is you choose an interpolation scheme. You don't need to, there is a default and that's what it uses. So, but then this you can specify in your input file. Okay. So you choose an interpolation scheme and then whatever you do, you write various constants to a field and then you are done. Then you go to init particles. Init particle is where you actually choose the initial position and the initial velocities for all the particles, okay? And there are many different choices already available. There is constant, constant 2, this way, that way, a lot of different things, okay? This is also quite straightforward.
Dhruva, one question.
Yes.
This
Yes.
inter percent, what kind of a type is this? I mean, inter, I saw.
That's, yes, see, that's the same trick that is used for the pencils also. Remember, all the pencils belong to a pencil class and they have these members. So the inter P is also like that and it has all these members. And that's how you access them. Was that clear?
Yes, yes. Thank you.
Okay. Okay, so there are now lots of different choices of initial condition. And these are all mostly copied from the particle dust. And this is where you see there is a problem with the code in the sense that there is a lot of duplicate code. So what should really be is that this part of thing should be cut out and put somewhere in some common place where it can be used both by the dust and the charged. But this has not been done. Okay, so all the particles are being assigned most of the time randomly this way or randomly that way. But then you apply the boundary condition on them. And then importantly, this is a variable, this is an array that is used quite often, which is called map nearest grid. So for every particle, you write down what its nearest grid point is, and this will, every particle will carry this index with itself wherever it goes. Okay, so it goes somewhere else, it actually updates the nearest grid and so on. This is very useful to know, because you can clearly see that that will be useful while interpolating. Okay. And then at the end of it, you sort the particles. So sort particles IMN. So this brings me to the other part of the pencil code, which uses the thing called the MN loop. So, okay, I can't see you. So can you take a quick vote and tell me what fraction knows about the MN loop?
Yeah, so we have to ask people to raise hands maybe. So people who know about the MN loop. Okay, people who don't know about the MN loop, raise hands.
Yeah.
I see one raise, two, three.
3, 4.
4 raised hands.
Oh, 4 people doesn't know about MN loop, about among 20.
20, yes.
That's not bad. So most people know about the MN loops.
Yeah,
So
but they are students using it, so I guess.
So let's use the general principle of teaching and completely ignore the people who doesn't know.
Actually, Dhruba, we also know the name, but we don't know exactly how it is done in the pencil code. Just recently, Philip has told us that when they're writing the for loop, the ordering of the for loop matters a lot for this cache efficiency. Okay. So if you could say
I will. I don't follow the general principle of teaching.
I had actually also asked Dhruva to cover this, but now he's being forced to cover it.
So, but you know why it is called the pencil code, right? It's a pencil code because we work in pencils. The idea is that, so I guess, so really has this been discussed, the pencil part of the pencil code and the cache and so on?
A little bit by Philip, yeah.
Okay, excellent. So if I say a few words, maybe it will be not too bad, because sometimes it's good to hear the same thing in different ways for different people.
Yeah, in lectures, repetition is best.
Yes, and there is also the elephant principle. That you see lots of blind men describing elephant. Okay, so the idea is that pencil code is mostly, we can use it in 2D and 1D, but the whole thing has been written keeping in mind 3D simulations. So now I'm going to talk very crudely. You see, if you had done things like Piali and me did when we were young children, like 8086 computing, then you would have a very good idea of how a basic computer works. So to add 2 numbers, it copies them from the memory to the CPU, adds them in the CPU, and sends the result back to the memory. So you see, these modern computers are extremely fast. So the bottleneck is not the actual floating point operation, but the bottleneck is copying the data to the CPU and sending it back. So to save that, the CPU also has a chunk of memory living on the same chip, and this is called a cache. And then there are different caches now, fast and slightly slower cache and so on. I'm not going into those complexities. But when you copy things to a cache, you don't copy a number, you copy everything around it. okay, a whole chunk of memory around it, with the idea that if you now do your computation such a way that it is local in your memory, then with one copy of the cache, you have a whole lot of things that you will work on and send all of it back. That way you save a lot of time by copying and copying back. And this will, of course, one of the things that will make your code really fast. So, and if you don't, then you will have things called cache misses. So if you profile your code, you can actually find out the number of cache misses that you are seeing. Stepping aside from that, so when the pencil code was first written, the size of the cache was not so large that it could fit the whole array. It never is. Because when the size of the cache can fit the whole array, then the memory is, of course, much larger, and we will be like to solving for much bigger size simulations. What could fit in the cache more easily was 1D arrays, something like arrays whose something like 512 cross 1. So this is why pencil code was constructed in pencils. So think of X, Y, Z, and think that I will go to one YZ point and calculate everything for one pencil, and then next YZ point and calculate everything for that pencil, and so on. Okay. So this going to every YZ point is what is called the MN loop. Because in the pencil code convention, your X is traversed by an array by a number called L, Y by M, and Z by N. Okay. So then you see, now you have another problem of how to deal with the particles which are lying all over your domain. See, if you start accessing how are the particles organized in the memory? They're organized by the particle index, right, to begin with. But the particle index and a particular region of the flow are completely decorrelated. So if you look at one particle at one corner, the next particle may be in a completely different place. And to study the evolution of that, you may need a completely different part of the flow. You see, then your memory access of the bigger array is going to be practically random. And that means things are going to be extremely slow. Okay. So that is why at this point, you sort your particles so that same M and N kind of falls in same place. You reorganize the particle in your memory, in the particle memory, so that the access of the particles and the access of the grid variables are kind of in sync. Of course, they will not remain in sync. You have to occasionally keep sorting them again and again. Okay, now this 5-minute long monologue, was that completely obscure or did something go across?
We did understand something.
Okay.
I think there
Okay.
is there a question?
Are there any questions?
Yeah, this is the time. Okay, Dhruva, but this is happening in init particles, right? But this will also happen after every time step.
See, if you do that after every time step, the sorting is expensive.
Ah, okay. So
Right. So you choose to do it after certain number of time steps.
Okay, okay.
And this sorting also is local in every processor. See, if you are doing multiple processor, then the sorting is in every processor. You understand, right?
Yes, yes.
Now there is, see, but this will give you another problem. Let's say you want to know how much you want to plot the trajectory of one particle, okay, at the end of your simulation. And let's say you have saved your snapshots. Now, if you plot the trajectory of the 5th particle from all the snapshots, you will not get the trajectory of one particle. Because which particle is actually the 5th particle is different at different times. You understand? So if you want to stick to one particle and calculate its properties, you have to be very careful in post-processing. Okay?
Yes.
Okay.
Yes.
So there is every particle actually carries one label, which was their initial label. So you could call them by that label. And one of the safe thing to do, for example, is to read the data in post-processing, sort it by that level, and only then deal with the data. Okay, but it will take a long time to discuss that in detail. So at the moment, let's go ahead, shall we?
Sure, sure.
Okay, so this is why the particles are sorted. Okay, now somehow I seem to have lost my connection. Okay. Okay, we are back. Okay, so then there is insert lost particles. Don't worry about that. Then there is insert particles. Don't worry about that either, because this allows you to insert particles anytime you want. Okay, and then comes that idea of pencil criteria particles. So this is important because you see, to calculate things, you may need to assume something already. So to be able to calculate the evolution of one particle in the charged way, you need to be sure that the pencil that contains the magnetic field and the pencil that contains the electric field are actually being calculated. Okay. See, these are the parts in each of the subroutines which keeps each other consistent. So here you see we are saying which kind of pencils are requested. Okay. So these two are said to be true. Then there is interdependency between the pencils, but let's not worry about that either. Now is the important point that you need to know. There is calculate pencil particles where almost nothing is important is being done. Then you have dxxp dt. Okay. So xx is the particle position, p means the particle. And you would think this is where the first equation is actually being solved, right? And you will be right. So you see, you are writing the right-hand side of the equation, which is dfp. And you are saying dfp is whatever dfp was plus the fp, because x dot is just equal to v. Okay. So this line here is just saying x dot equal to v. Is that clear?
Mm-hmm.
Okay. And you see that is only for the Cartesian coordinates. And this is being done if nx grid, there is points along the nx grid, if there is points along the y grid and so on. Okay. In cylindrical coordinates, things are different. And in spherical coordinate, things are even more different. You can imagine that. Because in the cylindrical and spherical coordinate, what you are looking is the second index, for example, in the spherical coordinate, is an angle. So you cannot, of course, step by an angle. It has to be r d theta and so on. Okay. So if there is a background shear, there will be extra term due to background shear. And then you come to dvvp dt. And you would think this is where the right-hand side of the equation is going to be solved. And then you will be wrong. Because now some perverse things are being done. And I will show you that part also. Why is something as perverse as I am going to describe being done? There is a good reason for that. I will tell you. Okay, sort particles, fine. So, okay, I already talked about this. I already talked about this. Now, importantly, dxxp dvvp dt dxsp dt, you already saw what it does. dvvp dt, at the moment, assume it does nothing interesting to our equations. But there are also two other functions, dxxp dt pencil and dvvp dt pencil. Okay. And what do they do? Actually, the dxxp dt pencil doesn't do much. Don't worry about that. Let's look at the dvvp dt pencil. Okay. This is the one worth looking at.
That's the non-relativistic equation.
So far, everything, I mean, everything is non-relativistic, yes. So it is just the equation that I wrote, E plus V cross B. Right? Okay.
If needed,
So,
it can be modified.
I'm sure, yes, definitely. So any equation you can put, you can change. You need a flag and then you can change it that way. Okay. But now look what is being done. There is a loop over all particles in the current pencil. Okay. So this routine is being called from the loop I talked about, which is the Amen loop. Okay, I will show you the hook where it stands in the code. And then you see what is being done. It's a loop over of K over K1 IMN to K2 IMN. Okay. These are, you imagine all your particles. And all your particles have indices. Let's say 1 to n. But now you think of one pencil. If you think of one pencil, that basically is one geographical region in your code. And K1 IMN and K2 IMN contains the first and the last index of all the particles within that pencil. You remember the particles were sorted by IMN. So
Initially.
I only need to know the first and the last one. The particles will keep being sorted. You see, if not at every time step, then every other time step and something like that. Okay.
So these are like name tags of the particles.
These are name tags of the particle in the current pencil, but I need to know only the first tag and the last tag.
Because
every other, because of the sorting, every other tag is in between. See, otherwise, I would need to have a list of tags, a number of tags, and this number will be different for different pencils, right? So it will be quite a strange array to keep track of.
Right.
Okay. Okay, so now I know the index K. So within this pencil, I'm going to the kth particle. And then there is this array I near grid, which from K gives me what is the nearest X, Y, and Z point. Okay. Once I know that, I interpolate. You can interpolate in many ways. Here, explicitly linear interpolation is being used. And by interpolating, what am I doing? So to interpolate, I need to give it the F array, which is the whole PDE. It contains all the variables in the grid. And then I say interpret the electric field from EX to EZ. Okay. Once you interpolate, so which point do you interpolate it to? You interpolate it to the kth particle's position. Okay. KIXP to IZP. When you interpolate, you will get a vector. Store that vector in the EEP. Okay. And there are these two additional things that are sent that are useful for the interpolation subroutine. Okay. This is how you interpolate the electric field, and this is how you interpolate the magnetic field. See, both of these assumes that the electric and magnetic field are known as an array. Okay. Otherwise, when you give these indices for the F array, you will get a floating point exception. Is that clear?
Yes. Okay.
Okay. Clear to everybody?
Yes.
Even those that are looking at their phones? Okay. So anyhow, so now I know the velocity. I need to know the velocity. Okay. This is the velocity of the particle. So this is FP I VPX to VPZ. This is velocity square. And then this is the maximum value of the velocity square. Now you remember particle radius. So particle radius is just a label. You just add a label to every particle, which is its radius. Okay. Why am I using that? Because I will use the radius to convert it into a mass. And from there, write a Q by M.
That's why you said it's a roundabout way of doing it.
Yes. But what's the advantage of this? The advantage is if I now choose a range of radius, I can choose a whole range of Q by M. If I want to run my simulations for different Q by M, but for the same flow, then I don't need to run many simulations. I just need to kind of divide my particle in different radius bins, and then everything will be taken care of. Okay. Now I have Q by M, and now I am calculating the acceleration. Now the rest of it, just few lines were there for testing. So there is a flag called only electric field. If you do that, then the acceleration is just Q by M multiplied by electric field. If you don't do, if it is general case, then you also added the V cross B. Okay, Q by M E plus F magnetic, and the F magnetic is the cross product of velocity and the magnetic field. Is that clear? You have the acceleration. Yes. Was there a question?
Yes, yes.
Yeah, Dhrubada, Shahil here.
Yes.
So I thought also actually you are using this radius maybe to incorporate this viscous drag term to the particle.
Absolutely, yes.
Okay.
See, for the viscous drag, you may want to have many families of particle, each with a different Stokes time.
Achha, okay.
Right. See, the Stokes time comes, every particle has a drag, which is like 6 pi eta mu, 6 pi mu AV, right? So if you change the A, which is the particle radius, then it will drag.
Okay. Okay.
And then you will get different Stokes numbers.
Right.
It's the same trick.
Okay. Okay.
Okay. Thank you. Good question. Anybody else? No. Okay. So then I have DFP, which is the whatever DFP was, plus the acceleration. See, the reason it is done this way is your DFP or the DF may have contribution from many different terms. Okay. So every routine that contributes to it, just add something to it. Okay. So the main part of the calculation is done. If you wanted to add Stokes drag, you can also do it here. Okay. So done. You have basically seen the main part of the particles charged. Okay. Let me just close this for a moment. Okay, so this is the part I just copied it to a slide. So the same things, interpolate, and the DFP is being added. Okay, so far everything is clear. Now let me show you the hook of where things are being added. Okay, so there is something called, okay, so quick question. Have you thought what is the most useful Linux command while dealing with the pencil code? Grep, absolutely, yes. Grep is your best friend.
Yes.
So start with equ.f90. Inside there is a subroutine called PDE.
Yes.
That's where the PDEs are actually being solved. Actually not, because inside there is something called RHS CPU. See, this is the part that came in the last 2 years or slightly longer, where there is also a GPU part of the code. Okay. So everything that I knew has been moved into this RHS CPU. Inside the RHS CPU, there is the MN loop. One of the few loops in the pencil code that are actually named. So if you search for MN loop, you will find it. inside the MN loop, you actually solve for every term in your equation, including this thing called particles PDE pencils. The particles PDE pencils called the dxxp dt and dvvp dt. And I have just described the dxxp dt and dvvp dt to you. Okay. So that's where the hooks are, and that's kind of what the structure of it is. Now I'm basically done. I just want to tell you one more thing. So this is, of course, when the flow influences the particle. What if you want to take into account how the particles influences the flow? Okay. First statement is, if you do that, physics-wise, you should be extremely careful. Be very, very careful, and then decide not to do it. Because the thing that you are giving back to the flow is a force which is concentrated at one point, right? Your particles are mostly point particles. So the force that is coming back to your grid is extremely singular. And you have to be careful about how this force is distributed back on the grid. If you choose one method of interpolation to find out the particles and use a different method of interpolation to put the effect of the particle back on the grid, you will not conserve momentum. And you may get complete nonsense. Okay. So how you do this, you have to do it very, very carefully. Okay. We have done this and other people have done this, and there is a long history of doing it in the pencil code. It is done, but do it carefully. This is the place where it is very easy to make mistake. Okay.
But this test particle method, it does
has
not
no
need
feedback.
No feedback.
Absolutely no.
So by default, the feedback is switched off. Or it
By
is not?
default, it depends on the subroutines themselves. In the charged, there is no feedback by default. So the feedback actually happens here. So again in the PDEs, you will find these lines where you say particle PDE or particle PDE block. This is where the force in the PDE due to the particles are calculated. So that's that hook. Okay. So equation PDE, the usual loop, and look inside the MN loop, you will find these few lines. Okay. Okay. That's, I believe, is all.
That has been tested for some year, or I mean, it is just
For the dust, this has been used a lot.
dust. So that is not charged.
No, that is not charged. For the dust, Anders has used it a lot. And Vlad has used it a lot, and their students and their collaborators have used it a lot. But every time this has to be done very carefully. So, okay, that's a long physics discussion. Better not to do it now. Okay, so that's it. Okay. So go forth and compute.
Okay.
Okay, yeah, thank you. So thanks.
Most welcome. So let me turn off the screen sharing and wait for questions.
Yeah. The screen sharing, maybe it will be from the slides. I don't know if there are questions.
Yes.
Yeah, there is one question.
Yes.
Yeah, Dhrubaditya, again, Shoail here. So I had one naive question. So regarding the flow, we control sometimes the stability part of the flows through this Courant number. So I'm just thinking in particles, is there any kind of
Absolutely excellent question.
Oh, okay.
Excellent question. If I should have brought some chocolates for you.
Okay. Thank you, Dhrubaditya.
So the time step is controlled. Yes, and I can show you where. So let's see. So you see the Courant condition is not really always the excellent estimate. Your code can be still messed up even if you satisfy the Courant condition.
Okay.
See, because there is Courant condition is like a dimensional estimate.
Right.
In dimensional estimate, you may have a number before it, which can be order 1. Now, so that basically means that number can be both 0.5 and 5. So depending on the problem, you should not satisfy the Courant condition too sharply. You should leave a kind of a gap. So this is where the CDT, CDTV and those things come.
Right.
Right.
Yes.
So for the particles, most of the time I actually choose the time step so that they are very small. I mean, depending on the case by case. But there is a way to estimate it. And let me see that. It should be in one of the earlier things. Oh, somehow I can't find it now.
Okay.
It's somewhere.
I'll check.
Okay, it's there.
Okay.
It's somewhere.
But it does have some number like C, D, T, C.
It should.
Or something.
Either it is there or it has been assumed to be 1.
All CDTs we have to search for.
Okay. Okay.
Yes.
I can check.
It is there. It is estimated. But you have to see every time you add a new term, you have to worry about the effect of that.
True. True.
Okay.
Right. Okay. Thank you, Dhrubaditya.
Thank you.
Okay, so this is whose hand? This is again Shohel's hand, right?
Oh, so I have to.
No problem. So Dhruv, I had one.
Nishchay. Oh, sorry. I'm sorry about that.
I had one question. So this actually Shohel pointed out to me from your talk that you were doing your simulation without the energy, without the entropy or temperature equation.
That's right.
So when you're dealing with reconnection and how particles are energized, so how much error are you,
Excellent question. I think quite a lot.
That we all ask very excellent questions.
Yes. So I think that's
one part. Then what would happen if you, or why is it?
So, but think of the following, right? So depends on what we are doing really, right? So if you are thinking of test particles, then, or you are already assuming they're not acting back on the flow.
Yes, true.
Right. So the reconnection is basically giving rise to these fast moving particles. So
which observers call non-thermal or what?
Exactly. And they will also give you thermal particles. But you are not taking them into account. But you can take it into account non-particle wise if you also solve the entropy equation. Because if you solve the entropy equation, then you know that the viscous heating is actually added to the entropy. And that can act, I mean, in principle, that can create flow.
Okay, so the viscous heating due to the particles, not due to the flow itself.
No, this is viscous heating due to the magnetic field. So not viscous heating, but magnetic heating. Joule heating, I'm sorry. I think of all of that just as dissipative heating. So not viscous heating, but Joule heating. See, because reconnection essentially is the effect of the magnetic diffusivity.
Right.
True.
Right. So then you get a eta J squared term. And if you include the entropy equation, that will typically be included.
So that will change it will heat.
But I suspect it will not do much. Because you see, you are always thinking in the limit of small eta. Of course, in the limit of small eta, eta J square is not 0.
No, that's
you see, you have to have a absolutely. You have to have a finite dissipation. But Okay, no. I expect it not to be important, but I can't give a good argument why. Okay, so this is just bias.
Yeah. Yeah, Dhrubada, if we just think of like problem like where shocks are there, so in front
Then
of
absolutely true. Then you are absolutely right, because you see the shock hitting is much larger, right? And but the shock hitting in the code is dealt differently.
yes, different.
In the shock module.
Yes, because the shock is dealt differently, and absolutely. Then say if you have shocks, then often it's the shock that controls everything. Right? Then of course, yes, completely.
No, but this pencil code, according to you, is it capable of capturing this Fermi acceleration through these shocks also? Is it capable of doing that?
I don't know. See, if you are going to look at this seriously, then I would say we can write a pencil peak.
Pencil?
Peak.
Pencil peak.
Pencil pick. Okay, PIC.
That's not too difficult, and that will be better. Okay, maybe different from the normal peak in the way that we will again deal with only vector potential. But I have to also read this recent 2021 paper that I was talking about, where they say that they do
something on Slack with you.
Sorry?
I shared something on Slack with you.
I have never used
Later,
Slack.
check it out. Later, maybe you can check it.
Yes, I have never used Slack. I will try.
Okay.
In Nordita, Slack is very popular. So a lot of people send messages and kind of, then that means I have to be on Slack all the time.
No, it is like whenever you see.
I will have a look. I will have a look. But so we had a whole set of notes for the pencil peak. Axel, me, and so on. And Philip. I can share it with you if you like.
Here, no? No, I don't see. They are still in the breakout room. Okay.
And I don't know if you maybe you didn't. We had a fellow at Nordita, Jonas Natila.
No, can't recall.
I think after your time. You were also a fellow, right?
Yes.
Yes. And so Jonas has worked a lot with peaks. He does one of the biggest peak simulations now. So I can certainly put you in touch. And his code is also publicly available.
I see.
And he is now in Columbia and Flatiron.
Flatiron.
Why is an institute called Flatiron? I have no clue, but never mind.
The mountains, I thought. Okay, I think we have to send a broadcast that we will close the breakout session in 4 minutes, breakout rooms, because there is Philip's talk on the radiation module. Actually.
Okay, so thanks very much for the time.
Yeah, thank you, Dhruva. Thank you for your time. And
thank you, and we can be in touch.
Yeah, sure. And if you can, I think you have already shared your PDF on Slack. If you can, that would be nice.
I will do that. I will share
both. Send it to me,
I
will upload to Slack.
Thank you, and I will share both the PDFs.
Okay, thanks a lot, Dhruva.
Okay, thanks very much. See you.